So we are happy to welcome today Claudio Quadrelli from University of Milano in Italy. He's going to speak about the Bogomolov conjecture, the Bogomolov-Positselski conjecture for maximal Galois groups. So please go ahead.
Thank you. Thank you for the introduction and also for the nice invitation. It's really a pleasure for me to speak here. And so today I will speak about the Bogomolov-Positselski conjecture, which is in fact, say, an informal name for a conjecture formulated by Leonid Positselski, but which is inspired by an earlier conjecture by Fedor Bogomolov and some related features of maximal Galois groups. And this is mainly a joint work with Thomas Weigel, but here and there I will mention also stuff done with other people and by other people. So in order to start, I would like to fix some notation. So first of all, P is a prime number, and in case P is equal to 2, I will often assume that I will often replace 2 with 4 because, you know, 2 behaves always in an odd way. So 4 is a better prime number than 2. And so given a field K, Kp will denote the maximal P extension of K, so the compositum of all P Galois extensions of K. And the maximal Galois group of K is the Galois group of the maximal P extension, and it is also the maximal P quotient of the absolute Galois group of the field K. And well, one of the main challenges in Galois theory is to understand the structure of maximal Galois groups of fields, and also to try to characterize them among the family of all P groups. And so finally, this P to the infinity root of K denotes the compositum of all this kind of extensions of K given by P to the n roots of the elements of K. Mu P to the F denotes the groups of the roots of unity whose order divides P to the F, and in case F is equal to infinity, it denotes just all these roots of P power order. And finally, ZP denotes the ring of p-adic integers, which is also the free cyclic P group, so the free cyclic group in the category of P groups. And we can see it as the set of P power series with coefficients in the finite field Fp. So all the talk will be, say, in the category of P groups. So closed subgroups will be intended to be as closed subgroups, and also generators will be, I will mean generators in the topological sense. So let's start with the original question by Fedor Bogomolov. So in the 90s, Bogomolov formulated the following question. So let K be a field containing an algebraically closed field. And let G be a Silov subgroup, a Silov subgroup of the absolute Galois group of K. Then the question is the closed commutator subgroup GK prime of G a free propy group. So this is the original question formulated by Bogomolov. Actually, in the rest of the talk, I won't deal with this question and similar questions related to the. I won't be dealing with the propy silo of the absolute Galois group, but rather I will turn this question in terms of the maximal propy Galois group of a field. So the question now becomes, is the commutator subgroup of the maximal propy Galois group a free propy group? So this is the question formulated by Bogomolov in terms of maximal propy Galois groups. Some years later, in 2005, Positselski observes the following thing. So, he observed that it is not necessary to assume that the base field K, capital K, contains an algebraically closed field. Sorry. The real important thing is that K should contain all the roots of unity of p power order. Indeed, okay, let's see what happens in this case. So in this case, we have that the quotient of, well, the abelianization of the maximal propy Galois group of K is the Galois group of this maximal p-radical extension of K over K. And by Kummer theory, this is a free abelian propy group. Okay, so the key point here is really the fact that K contains all the roots of one of p power order, so that we can apply Kummer theory. So the question now becomes whether the commutator subgroup of the maximal propy Galois group of a field containing all roots of one of p power order is a free propy group.
Sorry, is that the reason where P is 4? As is for that step?
Oh, well, no, okay. If P is 4, well, if P is 2, in this case, it does not change, but in the future, in the rest of the talk, I will assume that the base field K contains a root of 1 of order P. So if P is equal to, I will assume that K contains also the root of -1, which is the fourth root of 1. So, but this will be required in a while. So the question is GKP. So in this case, P is really 2, but P equal 4 means that we need to assume that K contains also the root of -1 in case P is equal to. So is the commutator subgroup free? And but now it makes sense to ask the same, to think what should be the question now if K if the base field K does not contain all roots of unity of P power order, but if K contains at least the roots of unity just of P, of order P, and also the square root of -1 if P is equal to 2. So in this case, the situation is as follows. The Galois group of the maximal P radical extension of K, so we can, since K contains the roots of 1 of order P, we can still apply Kummer theory. And now, by Kummer theory, the Galois group of this extension splits as a semi-direct product. So it is no more abelian, but it's quite close to an abelian P group. It is the semi-direct product of the Galois group of this maximal P radical extension over K adjoint with all the roots of 1 of P power order. And this guy is free abelian. With the P cyclotomic, the Galois group of the P cyclotomic extension. And this group is propicyclic or trivial if K already contains all the roots of 1 of P power order. So this group is it is not abelian, but it's not so far from being abelian. So now the situation is the following. So we have the maximal P extension, then the maximal P radical extension, the P cyclotomic extension of K, and the base field K. So this is either propicyclic or trivial. This is free abelian. And now, what is this? So the question, the conjecture formulated by Positselski, which is inspired by Bogomolov, is the following. Is the Galois group of this extension here a free P group? So, and this is what I will call the Bogomolov-Positselski conjecture. So let me remind you that here we are just assuming that K contains the roots of 1 of order P, and also the square root of -1 if P is equal to 2. Okay, so now I would like to give a group theoretic translation of this conjecture in order to be able to work with this conjecture in purely group theoretic terms. So, oh, by the way, first of all, I would like to observe the following. So I will call this. So here we have the Galois group here is the maximal pro P Galois group of K. And I will call this Galois group just G bar for simplicity. Okay, first we need an observation. We have that the first cohomology group of G bar with coefficients in the finite field Fp is isomorphic to the first cohomology group, again with coefficients in the finite field Fp, of the maximal pro P Galois group, again by Kummer theory. Because by the Kummer isomorphism, both cohomology groups are isomorphic to this quotient. So the units of K modulo the units of K to the P. So both cohomology groups are isomorphic to this quotient. And so in terms of groups, this means that, roughly speaking, these two groups, G bar and the maximal pro P Galois group of K, have the same generators. Okay, so so another way to say this is to say that the kernel of the restriction from the maximal pro P Galois group and the group G bar is contained in the Frattini subgroup of GKP, which is the closed subgroup generated by P powers and by the closed commutator subgroup. Okay, now let's try to translate this question in purely group theoretic terms. And in order to do this, so here a key point is that we have so the maximal pro P Galois group of K surjects onto this this Galois group, which is free abelian by cyclic, and as I have just said, the kernel of this epimorphism is contained in the Frattini subgroup. So the generators of this are the same as the generator of all this group. Okay, so I want to translate this thing in purely group theoretic terms. And therefore, I give the following definition. So first, let's take G, let G be a pro P group. We say that G is Kummerian if the following conditions are satisfied. So G has an epimorphic image, G bar, which splits as a semi-direct product as the Galois group above does. So where A is free abelian and Z is either cyclic or trivial. And the kernel of this epimorphism is contained in the Frattini subgroup of G. Oh, by the way, I didn't say that here, the action of the Galois group of this semi-dark product is given by the cyclotomic character. So this factor on the right acts on the factor on the left by the multiplication with 1 plus p to the f, where p to the f is given by the roots of unity of p power order contained in the base field K. So we are this situation mimics the Galois the situation in the Galois theoretic case. So also here we require that the left factor acts on the right factor by multiplication with a p-adic integer. So one plus p to the f. In case f is infinity, it is just the trivial action. And so this is the first rough definition. And Kumerian propy groups were introduced by Ido Efrat and myself a few years ago. The original definition is not this one. And this property can be given also in cohomological terms. I will do that soon. But well, this property can be formulated in several ways. And this is the best way here in the setting because it really mimics the situation in Galois setting. So this is the first property. And we say that G has the Bogomolov-Positselski property if the kernel of this, let's give it a name, the kernel of this epimorphism is a free propy group. Which is precisely what the Bogomolov-Positselski conjecture ask about in the Galois theoretic setting. So, well, oh, by the way, this condition, the Kumerian property, is also related to smooth profile groups, which have been introduced by Mathieu Florence, who gave a talk a month ago, and later I will explain how. But first of all, okay, I would like to give a few examples of propy groups which do not have the Kumerian property. So you may ask how restrictive is this property? So this property, by what we have just seen, this property is satisfied by maximal propy groups of fields containing a root of 1 of order P. So this is a property enjoyed by maximal propy groups, and it's interesting to see how restrictive is this property. And I give you just an example, an easy example of a propy group which do not satisfy this property. So let G be the group generated by X, Y, and Z, satisfying this condition. The commutator between X and Y is equal to Z to the P. This is not Kumerian. And another example, let's take again a propy group generated by 3 generators with these 2 relations. So the commutator between X and Y is equal to Y to the P, and the commutator between Y and Z is equal to Z to the P. Okay, also this is not Kumerian. And well, the Kumerian property, if used also in depth, can be employed to fish a lot of concrete examples of propy groups which cannot occur as maximal appropriate Galois groups of fields, and therefore also as absolute Galois groups. So even if the covariant property may seem not so surprising, actually it is quite restrictive. And
could you remind us what G bar is in the definition?
Here in the definition is just a propy group. Okay, I can even, maybe it's better if I omit this and just assume that G surjects on a propy group which splits as a semi-direct product in this way with a free abelian factor and a cyclic or trivial factor. So which is precisely what happens when so this is isomorphic to the Galois group of this maximal periodical extension of K. So just to remark that we are really making the group theoretic copy of what happens in the Galois theoretic case. So
it could be the trivial group?
Yes, possibly, but this necessarily means that also G is trivial, because this condition means that G and the epimorphic image have the same generators. So if the image is trivial, also G is trivial. Okay.
Okay, got it. Thank you.
Oh, thank you for the question, which helps to clarify what I mean. Okay, so in order to express the Bogomolov-Positselski conjecture in a more effective way, I need to introduce another tool.
Sorry, I have another silly question. Yeah. How do we know that in those examples, the groups are not covariant?
Oh, okay. So in fact, there is, okay, thank you for the question, because it let me underline who is the actual father of this property. Okay, I will explain very briefly, but first I need to introduce a tool. So this can be shown also using cohomology and using a property discovered by John Laboute from Montreal, who should be credited as the real father of this condition. So, but first I need to introduce one other thing in order to give the cohomological translation of this property and explain all this. So if we have a homomorphism from a propy group G to this semi-direct product, we can define a homomorphism of propy groups from this quotient to this group. How? So we define theta bar of G to be lambda such that where G belongs to G belongs to this semi-direct product, such that so this theta should describe the action of the factor Z on the factor A. So G to the -1 is equal to A to the theta bar of G for every A in the free abelian factor. Okay, so this map describes the action of the semi-direct product. And so if G is covariant, then we can take the composition of these two maps. So this is the epimorphism phi, and we define this theta from G to this group 1 plus PZP to be the composition. So theta is theta bar composite with the epimorphism. And in general, we can restate the Kumerian property as follows. So G is Kumerian. Oh, sorry. If and only if there exists a map from G to 1 plus P ZP such that the following cohomological condition is satisfied. For every positive number, this map in cohomology from ZP theta modulo P to the N to this, the first cohomology group with coefficients in FP, is surjective. And this module is, this module is isomorphic to the ring of p-adic integers as a abelian group, and the action is given by this map theta. Okay. So this the surjection from this module to FP induces a map in cohomology, which a priori is not surjective, but if this is surjective for every positive integer n, then G is Kumerian. So the Kumerian property can be translated in these cohomological terms. And so this is the same definition of smooth profile groups as used by Mathieu Florence. But as I said, in fact, this property was used first by John Labute in his PhD thesis, where he classified the Mushkin groups. So in fact, John Labute proved that there exists a unique, for the Mushkin group, there exists a unique map theta like this, such that this property is satisfied. And I will stress that he should be given the credit for the invention of this property. And so just to answer the question, also John Labute showed that this property is satisfied if and only if 1 cocycles of G with image in FP can be lifted as much as possible. And so in these groups, it is not possible. So it's quite technical, but it's not that difficult to show that it is not possible to lift 1 cocycles for these groups from FP to a higher module, and therefore this cohomological condition is not satisfied for these 2 groups. Okay, so okay, so this cohomological condition is the cohomological version of the Kumerian property, but this let me also define the other main character of my talk, which is the elementary type conjecture and property groups of elementary type, which is due to Ido Efrat. Okay, we say that that a property group G together with a map theta like this. Oh, and by the way, if a property group G is Kumerian, then this theta coincides with the composition of the theta bar given by the epimorphic image, which splits as semi-direct product. So in general, we call a couple of propy group G together with a map theta, which is just a morphism of propy groups like this, we call this an oriented propy group. This definition is necessary to define elementary, the elementary type conjecture and propy groups of elementary type. So the family of propy groups of elementary type which was defined by Ido Efrat, is the family of propy groups which can be constructed iteratively in this way. So is the smallest family containing free propy groups with any arbitrary map theta. F is free. And the Mushkin groups and theta is the canonical map as defined by Labute. So in case G is the maximal propagula group of a local field, then theta is the cyclotomic character. Okay, so these two families of groups are the building blocks of the family of propy groups of elementary type. And how do we assemble them together? We have two operations. Well, the first operation is free products. So, which is defined as the free propy product of propy groups. And theta for this new free product is defined using the universal property of the free product. And the other operation we can employ is the semi-direct product with ZP with action given by the map theta attached to G. So we start with these bricks, free propy groups with arbitrary maps theta, and the Mushkin propy groups with their canonical map theta, and we assemble them using free propy products or the semi-direct product with a cyclic factor with action given by the theta of the group G. So And the conjecture formulated by Ido Efrat is that G together if the maximal propigal group of a field is finitely generated, and K contains the roots of 1 of P power order, and also minus the square root of -1 if P is equal to 2, then the maximal propigal group together with the P cyclotomic character is of elementary type. This conjecture is still widely open. Still, we know that it is verified for some relevant cases, such as, well, local fields, of course. We have free groups and the Mushkin groups. Also for pack fields, for algebraic extensions of global fields, if they are finitely generated, and also pure rigid fields. So there is a number of relevant cases where this conjecture is verified. And well, most importantly, we do not have concrete examples of propy groups which satisfy this the Kumerian property and which are not of elementary type. So all propy groups, all Kumerian propy groups. Okay, well, actually this is not true. I should say all smooth propy groups. Smooth propy group means that every subgroup is Kumerian. So the smoothness property of Florence is hereditary Kumerianity. So all propy groups whose subgroups are Kumerian are of elementary type. And this is quite important because let me remind you that this property, smoothness, is a property enjoyed by maximal propigal groups. Okay, so now I have all the ingredients to state the main result I want to show, and which is a result by myself and Thomas Weigel, which has been just published.
Sorry, I didn't quite catch the relationship between the conjecture and the statement that you wrote after the conjecture.
Yeah, sorry, I didn't write it very well. Sorry, because I put the things together. I want to say that all the examples of propy groups which are known to be hereditary Kumerian or equivalently smooth. Okay, so this is not the theorem. Oh, the propy groups which are known to be smooth, which is equal to every subgroup is Kumerian. Are of elementary type. So we have no examples, no concrete examples of property groups which satisfy this property and which are possible candidates for being realized as maximal property Galois groups of fields, which are not of elementary type. All possible examples we can construct which satisfy this property are of elementary type. So which is at least a strong hint for the validity of the elementary type conjecture. So the conjecture is still widely open, but there are some hints which suggest that it is not such a big gamble. I hope it is clear now. Sorry, I'm aware I didn't write it very well.
But it may also suggest that there aren't many known examples.
Yeah, that's true. But there are some concrete examples which may look, indeed, one of the branches of the research in this line is to find explicit, concrete examples of property groups which are not maximal property groups. And a lot of examples of this kind do not satisfy this property. So there are some interesting examples of property groups which are known not to occur as maximal property groups, and they are not of elementary type. So there are some hints coming both from the known examples and both from the examples. Yeah, it's true that the known examples are many, but using also these properties, it is possible to construct some examples of property groups which do not occur as absolute Galois groups. And there is a lot of research on this line, and we are collecting some hints, at least.
Thank you.
Thank you for the questions. So now the theorem. So but I wanted to say here is to convince you that even if the conjecture is open, if you want to check which is conjecture to hold for maximal Galois groups of fields, first you should test this property for property groups of elementary type. So this is the first thing you should test when you formulate a conjecture on the structure of maximal property Galois groups. And this is precisely what I have done with Thomas Weigel. We proved that property groups of elementary type satisfy the Bogomolov-Positselski property. So this means that this property is true for all the fields which are known to satisfy the elementary type conjecture. So as I said, for example, we have, well, 1F fields. Well, this is not a very relevant example, but we have also pseudo-algebraically closed fields, local fields, and also algebraic extensions of global fields. Such that the maximal property Galois group is finitely generated. So indeed, the elementary type conjecture is formulated for maximal property Galois groups which are finitely generated. and also p-rigid fields. So these are some of the fields which satisfy the elementary type conjecture. And therefore, we have that the Bogomolov-Positselski conjecture holds true for all these examples of Pro-P groups. Well, the main tool here is to show that the Mushkin groups satisfy the Bogomolov-Positselski property, but this is not that difficult because it is very well known that all subgroups of the Mushkin groups of infinite index are free groups, and to show that the Bogomolov-Positselski property is preserved by the two group theoretic operations which are employed to construct Pro-P groups of elementary type. And we prove also another little result, which has less consequences in comparison to this, but which is also closer to the spirit of original question by Bogomolov. So if K is a field containing root of unity of p-power order with this quotient finite, K should contain all the roots of unity of p-power order, and the p-power, the p part of the Brouwer group of K has rank 1, then also in this case, the Bogomolov-Positselski conjecture is true. And I would like to conclude with a mention of the possible relation between the Bogomolov-Positselski conjecture and the Bloch-Kato conjecture. Indeed, okay. Let's consider the Galois group of the maximal periodical extension. So as we know, this splits as a symmetric product this way, and the cohomology algebra of this Galois group is the exterior algebra generated by degree 1. And so the exterior algebra is generated by elements of degree 1, of course. And so all the elements of the exterior algebra are symbols. And if the Bogomolov-Positselski property is true, then we can consider so the Hochschild-Serre spectral sequence Okay, let's call this G bar. And so we can consider the spectral sequence of the cohomology of the maximal propicular group of K. Well, if this is true, if this is free, which is what is conjectured by the Bogomolov-Positselski conjecture, then it has cohomological dimension equal to 1. Which means that all these guys are trivial for T bigger or equal to 2. And by this spectral sequence, we have that the cohomology algebra of the maximal propicular group with coefficients in Fp is a quotient of the cohomology algebra of G bar, which is the exterior algebra generated in degree 1. And therefore, so since all the elements of the exterior algebra are symbols, also all the elements of the cohomology algebra of the maximal propicular group would consist of symbols. So the Bogomolov-Positselski property could provide a way to find a new proof for the Bloch-Kato conjecture, alternative to the one by Rost and Voevodsky. And so this is all I wanted to tell you. So thank you for your attention.
Oh, sorry, maybe you did not order me. Do you have
Oh, no, I didn't.
questions?
Sorry.
Questions or comments for Claudio? Please go. So you can use the chat if you have no microphone. Oh, okay, so I have a question. So in your main theorem, what about the case of higher local fields?
Well, higher local fields. Okay, in case of higher local fields, we didn't consider higher local fields, but I guess I may be wrong, but I guess it shouldn't be that difficult because I think that the maximal propicular groups should be constructible using the semi-direct product.
Okay, so you have a transition statement, something like that. So if, for example, if you know the result for K, do you know it for yes. Laurent series?
Yes, yeah, we do, because in this case, so in the case of this semi-direct product, the Bogomolov-Positselski property is preserved in a almost trivial way, because so if it's almost immediate to see that not really immediate, but we can show that if G satisfies the Bogomolov-Positselski property, then also the semi-direct product satisfies. Well, and the reason
okay,
is
thank
that,
you.
Okay.
Yeah, yes, but you know, well, so this is with the Lorentz series. This is the easy case, but you know, higher local fields, you know,
Yeah, it's not that easy. So
you can have, you know, much more complicated things, you know, involving wide inertia and so on. Okay, so
yeah, sure. So in this case of Lorentz series, it works. We did not consider the question about higher local fields, and yeah, of course, it would be interesting to think about this in the future. So maybe this could help. Maybe it's not that easy. So.
No, I don't know. I mean, you know, because you have this big thesis by Kazuya Kato, you know, in the 70s, where he proved Bloch-Kato conjecture for those fields, for example. You know, and it was I mean, it's an art thing, you know.
Yeah. So
okay,
I cannot answer.
No, but that's good. That's good. Thank you. Other questions?
So on this last slide, I didn't quite follow. Are you saying that the Bloch-Kato conjecture follows from Bogomolov-Positselski?
Well, not completely, because the statement of the Bloch-Kato conjecture is more general, but at least a part of it. So the hardest part of the hardest half, say, of the Bloch-Kato conjecture is to show that the elements of the cohomology, well, in fact, the statement of the Bloch-Kato conjecture is about cohomology with coefficients in. So Bloch-Kato is about cohomology with coefficients first we have the whole Absorb group, and we take these coefficients. So, but the hardest part is acknowledged to show that all the elements of this cohomology are symbols. So this is what expert says, and I trust them. So this is the hardest part, and this is sorry, my tablet has just fallen. So to show that even just the elements of the cohomology group with coefficients in FP, to show that these cohomology elements are symbols, could help to get the hardest part of the conjecture, even if maybe not in the most general statement, but at least in the statement, so with coefficients in FP. And so this could be a possible way to attach the conjecture, I mean, to provide another proof of the conjecture. So already showing that the elements of this cohomology algebra are symbols would be quite an advancement. To provide the proof of this fact without Rostov-Blavatsky proof.